All right.
I'm just going to ignore them.
So, yeah. So today we are continuing with our kinematics stuff. And then we're looking at velocity and acceleration. So velocity first up. And so velocity, we're looking at velocity as rate of change in position. Alright, so rate of change in position. So when we're talking about a rate of change, we're talking about a derivative. And with this kinematics stuff, the thing that links all this together is time. So we're looking at a derivative and time. So if the velocity then is some function in time, or position I should say, then the velocity is also the rate of change of position with time. And if we've got velocity written in terms as a function in terms of position rather than time, these two things need to be the same. And so what that means then is dx dt is a velocity function in terms of position. And then to solve this, we need to do the derivative, the flippity flip, alright, because here it's a function velocity in terms of position. Alright, so we've got to do the antiderivative in terms of x, not in terms of t, so we've got to flip one on fx, and then of course now we can do the antiderivative with respect to x, and so then we can find an expression. So let's have a look at a couple of examples. Alright, so we've got a particle, and the particle moves in a straight line. Such that its velocity in terms of its position is 1 on x plus 2 centimetres per second, and of course x can't be -2, can't be at negative, or in fact can't be -2, but we've got a further restriction here on this, in that x is greater than -2. All right. And what we also know is we know that when t equals 0, so it started at position 0. All right. So there's some things we want to find out here. First of all, we want to find the position as a function of time. We want to know then from that, the position at t equals 2.5 seconds. And then C, we want to know the distance travelled in the first 2.5 seconds. All right. So what we've got to do is, here it's asked the position as a function of time, but we've got velocity as a function of its position. So we need to be using this relationship down here to help us find the position as a function of time. We've got to bring time into it. And so the way we bring the time into it is that our velocity is dx dt. All right, so let's work through that. All right, so our solution. So velocity, as I already mentioned, is dx dt, and in this case, our velocity is given to us in terms of its position. So, as I already mentioned before, for us to anti-differentiate, because this is position, we've got to anti-differentiate with respect to x. So what we do here is we flip, so dt on dx, and 1 on x plus 2 becomes x plus 2. Yep. All right, so now we can anti-differentiate. Time would be x plus 2 dx. And the antiderivative of that is x becomes half x squared, 2 becomes, and we've got some constant. Now we know some information to help us find the constant. So when t equals 0, x equals 0, so if we substitute all of that in, our constant is 0. So we have time equals a half x squared plus 2x. All right, what are we going to do with that? Because the question asks us to give the position as a function of time. So we want x equals something with time in it. All right. What are we going to do here? Any ideas?
Take that on the back of the bed. No?
It's an idea, but it's not going to help us. So we've got x in 2 places. If we take it out, we've still got it in 2 places. So we need to get it down so we have x appearing once. Let me times everything by 2. What could I do with this, do you reckon? So that I get x appearing just once. Complete square. Because in here we're going to have x plus 2. Now, of course, when I do that, I've now created an extra 4, so I've got to take 4. Alright, so this 4 here comes about when we expand that, and so I need this minus 4 here to keep it balanced. Alright, so now we can rearrange. Alright, so if you have something like this where you've got x in 2 places, we need it once so that we can write it as x equals. So a common strategy for that is to complete the square. Alright, so now we rearrange a bit. Add 4, square root, take 2. Alright, so what did I say? Add 4, so 2t plus 4. X plus 2 squared. Square root. So when I square root, plus or minus, is that correct? Or is that incorrect?
Incorrect is the function of time, so you can only have positive.
Yeah, can only have positive, but that gets back to our original restrictions on the Vx equals 1 on x plus 2. Our restriction on x was x had to be
Less than, greater than.
greater than negative 2, didn't it? So if x is going to be greater than negative 2, can we have both of those? No, we can't, can we? Which one is the one that we can have? The positive one, yeah. Alright, so this one's out, because x has to be greater than negative 2. That was our original condition that we had. Alright, and then we take 2 away, so minus 2 plus the square root of 2t plus 4 is equal to x. Alright, because if we had the negative, it would be less than negative 2, wouldn't it? Taking more away. Okay, so there's part A. Part B, what did part B want to know? Part B wanted to know where it was after 2.5 seconds. So that's simply a matter of substitute, yes? Negative 2 plus the square root of 9, yep. Negative 2 plus 3. It's at 1, and it's centimetres, isn't it? Wherever 1 centimetres is, that's where it is. Alright, so the distance travelled. So in this case, the distance travelled in that first 2.5 seconds. So at t equals 0, it was at x equals 0. And t equals 2.5, it's at x equals 1. Our function with the t in it is what sort of function is this? Square root. Yeah, it's a square root function. So, a square root function goes like that kind of shape, doesn't it? So as time goes by, we're always getting further away, aren't we? because we're always getting further away, v is always positive, because x is always greater than -2. Velocity is always positive, so it's always heading in the positive direction, or it's like that as well. So the distance that it's travelled is 1 centimetre. So if this here was quadratic or something like that, maybe it might go out and then head back, but in this case it's always heading out. Alright, so that's velocity. And we can look similar with acceleration. So in this here we had velocity in terms of its position. But we could have also acceleration in terms of velocity, and that's what we'll look at now. And then we employ, the same kind of strategy to bring the time in. Alright, so acceleration. There's rate of change. Velocity. Alright. So if acceleration is in terms of velocity, that is A equals some function of velocity. Can I use G here so we don't get confused from what I did before? Is that all right? Some function in terms of the velocity. But we already know that acceleration is the rate of change in velocity with time. So again, these two things have got to be the same. And so dv dt is that function velocity. Again, we've got velocity, so we can only anti-differentiate or differentiate in terms of velocity. So we need to flip. And so then anti-differentiate with respect to the velocity, and then if we need to, do what we did before and rearrange stuff. Alright, so let's have a look at an example. Alright, example. Alright, so the acceleration, which is dv dt, is in terms of velocity, v. At time 0, body's at rest. At the origin. Find as a function of time all right. Okay, so when we look at this, obviously important bits. That part's obvious, dv dt, v plus 1. We also have two other bits of information. So t equals 0. The body is at rest at the origin. So rest is v equals 0. The origin is x equals 0. Alright. So we're going to use these bits of information, not all of it all at the same time necessarily, when we're doing these things. Alright. So the first one is to find the velocity as a function of time. And so we have, for A, we have dv dt equals v plus 1. First step is to flip, yep. Then anti-differentiate. So we've got 1 over v plus 1. So that relates to everyone's forgotten.
Log.
Log, thank you. Yep, no squares here. If there was squared in there, it might relate to tan, inverse tan, yeah. But there's no squared there, so it relates to log. And so that would be log base e, the magnitude of v plus 1 plus some constant. All right. To find the constant, we've got some information. And the information we have is that at time equals 0, what do we know about v? V equals 0. So 0 equals log to the base e, 0 plus 1 plus c. So 0 equals log to the base e of 1. Actually don't need those signs, but anyway, it doesn't matter. So the constant would be 0 because log to the base e of 1, or log to the base anything of 1 is 0. Alright, so now we've got then that t equals log to the base e and v plus 1. Alright, we need to get velocity as a function of time, so we need to get v equals. So what are we going to do here?
This power of E.
Power of e to the power of, yeah.
Power.
E to the t would be v plus 1, which would mean that v is
E minus 1.
yep. There we are, done. All right, part B says the acceleration as a function of time is what we want. We already had the acceleration up here as a function of the velocity, but we wanted it as a function of time. So what do we have to do? V is,
Differentiate.
V is, I'm getting ahead of myself here, I don't want that there. Yeah, acceleration is dv dt, isn't it? So we simply need to differentiate that. And so when we differentiate e to the t minus 1, what do we get? E to the t. Alright, the next bit that we want is the position as a function of time. That's where I was getting ahead of myself. Before, or C, not B, where I was getting ahead of myself. Because V is dx dt, isn't it? Which we know is e to the t minus 1. So what do we need to do to find the position? We just need to anti-differentiate with respect to time, and we can do that because it's already in terms of time. And so e to the t becomes
E to the T.
e to the t. Oops. Minus 1 becomes plus some constant, and we know that when t equals 0, the position was 0. And so C is -1, yep. So our equation is e to the t minus t minus 1. Alright, anything about any of that stuff? Alright, that's it. 10D.